Oh wait, there. Welcome to the Robotics Institute seminar, the Robotics seminar. We're very lucky today to have with us Volkan Isler, who's here from the University of Minnesota. Let's see, Volkan's what he did his PhD at Penn and worked in the GRASP lab, and he went and did a postdoc with a bunch of do-gooders at Cal Berkeley, CITRIS, with Regina Bacci, the Boston. Yeah. And he's still doing good. I guess it's permanently worked. Doing some things with the environment, and but I'll let him tell you about that. So please join me in welcoming Volkan Isler.
So thank you, Matt, for the introduction and for hosting my visit, and thank you all for coming to my talk. It's been a super fun day, very stimulating discussions. So I'll talk about, I already got quite a few questions about what I mean by the wild, so I'll probably disappoint some of you. So I'll talk about our work on basically using robots as data gathering devices. And the talk is essentially kind of a sampling of things that we have been working on, with a part in the middle where I'll just go over one of the more recent results on a new coverage problem. And this is my lab. We do both some like algorithmic, foundational work on sensor planning, pursuit evasion types of problems. And more recently, we've been focusing on environmental monitoring and agriculture applications. And it goes without saying that this is the not only the brain, but sweat, sometimes blood, often frost bites of these folks, and I'll give individual credit. But this is the batch that mostly graduated, and they focused on environmental monitoring applications. And this is the current group who's mainly focusing on agriculture. So I'll kind of use the field applications to motivate some of the problems that I'll introduce, and then get into the details. So one of the biggest projects in my lab, which we're about to wrap up now, is on carp. How many of you are familiar with the fish carp? Okay, quite a few. If you're not, it's just a fish. But depending on where you are, it's considered invasive. And why it is invasive depends on the region too. I actually didn't know much about carp until I moved to Minnesota. But around that time, I actually saw this newspaper article. So what happened in Chicago is they found one fish in the canal, and they basically poisoned a 6-mile stretch to prevent the fish from entering the Great Lakes, because there the concern is that it can take over the habitat and destroy the fishing industry there. So just to show you the significance of the problem. So this is the river version of the fish. There's also a lake version, and one of our project partners is the Malheur Wildlife Refuge. So this is in Eastern Oregon, and just to give you a sense of scale, it's about 20 kilometers in diameter. It grows and shrinks. So this is a bird sanctuary. So people go there to see the birds and so on. And what happened here is, to attract more tourists in the 50s, they introduced the carp. And then the carp started eating the bugs that the birds should be eating. So then the birds left. So then it became this big problem, because now less tourists were coming and the birds were not coming. So the refuge management does a lot of work on cleaning up carp. And one of the things they did back in '92 was drastic things like blowing up the place. Rotenone is some kind of chemical, and then scoop up, and this way, even though they, catch hundreds and maybe 500,000 fish, the problem is they can't find their spawning locations, and then they just come back and so on. So I work with a fish biologist, Peter Sorensen, also at the University of Minnesota, and they study carp behavior. And what they do is, so they catch the fish live, and then the tag there, it's about the size of a AA battery. So they, by surgery, they insert the tag in the fish, and then they release them back in the water, and then they try to track the fish to understand its behavior. And one interesting thing is these tags, to make the batteries last long, they actually work at 1 hertz, the signal, so they beep at once a second. So this way, the battery lasts for about 2 years or so, which will be significant. But what Peter Sorensen and his group showed is things like this. So these are the locations of about 20, I think, fish in April. You see they're all over these 3 connected lakes. And then in January, they aggregated. So then what they showed is like the fish often aggregate, and if you can find these aggregations, then all you have to do is just call the fishermen, and then they can just like scoop up hundreds and thousands of fish. And this has been like successfully applied in many different lakes. So this is what they do. This is kind of the application of what they do, and then on the scientific side, they also try to understand when these aggregations occur, what are the underlying conditions. And of course, as roboticists, we just try to automate the kind of thing that they're doing. So this is usually the work of like 2 researchers. One of them steers the boat. The other one rotates the directional antenna, which gives you the bearing toward the fish, and then when the signal is strong enough, they just record the GPS location. So that's the resolution. And our job is to automate this task and maybe more accurately track the fish. So I used to show this picture and move on, and then I realized that there was no sense of scale. So are these like this big or this big? So the boats are pretty large. They're about 6 feet. And this is mostly the work of Pratap, who is now at Virginia Tech, and Josh, who is now at JPL. So I'll first give an overview of some of the problems that we've been working on in this context. So our first task is to find the signal, okay? Because when the boats are on the water, you may actually not even hear the tags. So then we treat this as a coverage problem by treating the fish mostly as stationary. And then we have this algorithm where you input these rectangular regions, and then the boat finds an optimal path or close to optimal, and then goes and finds the fish. So this stage, I think we can do this like pretty robustly for a couple of hours, basically until the batteries last, and then find the tags. So this one was for like about an hour, and we did about 5 kilometers. So the interesting coverage problem here is geometrically, if you have a polygonal area and then these convex objects touching the boundary, it turns out that the optimal order to visit them is given by their order in the boundary. So you never have reason to crisscross. And this actually yields a very efficient coverage algorithm. You just visit them in the order they appear, and then go and cover them. And we were able to like analyze how far we're off from the optimal and so on for this problem. So this is an example of like what we computed. And then this is the execution of this trajectory. And those you see over there are the unique frequencies, unique tag numbers of the fish. So here we had like an aggregation in this case. Okay, so this was the first task, just to find the signal. Okay, but we can do more. So if we rotate the antenna, right, we can get a very coarse bearing measurement to the target. And one thing again interesting in this case is, so let's say like you sample 18 angles, and then you take 5 measurements at each angle, then it takes about 2 minutes to get one bearing measurement, and the uncertainty is about like 10 degrees or so. Okay, but what you can do is, let's say you get this one, and then this one, and then you intersect these measurements, and this gives you a much better localization of the fish than the sensing range. So let's look at this uncertainty about the localization. It's one way of quantifying it is given by the GDOP, geometric dilution of precision, and it is proportional to the product of the distances. So close is good, but it's also a function of the angle, right? Because if you see, like if the angle is 0, then you get infinite uncertainty, or if it is 180, the uncertainty is large, whereas 90 is a good angle. So this turns out that it's proportional to 1 over sine theta. Okay. So the problem that I want to talk about today is a data gathering problem where we want to collect data to do this type of localization well. So formally, it's something like this. So I give you candidate target locations, which could be just continuous subsets of the plane. Okay, and then I also give you a measurement threshold. So I want my uncertainty to be at most U star. Okay, and the uncertainty is given by this. What I would like to compute is a tour and also measurement locations along the tour, so that no matter where the target shows up, I have at least 2 measurements which are good, in the sense that this evaluates to something less than U star. Okay, so like in pictures, these are the regions that the fish could be at, let's say, and we compute this tour and these sensor measurements such that no matter where the target shows up, there are 2 measurements, let's say this one and this one in this case, and this is less than U star. Is the problem clear, or are there any questions about this? Cool. Okay, so then I'll just present an approximation algorithm for this problem. Okay, and we'll go through a few structural results. So this is the part of the talk where I need your attention. So here's the one thing to think about. So if we go back to this this measurement function, it's a little bit tricky because it doesn't require both of the measurements to be close, right? It could be that one of them is close and then the other one is far, but the product itself evaluates to something less than U star. Okay, and also the relative location of the targets is different, but we can show that at least one of the measurements has to be close. Okay, so the observation is relatively simple. So again, U star is the uncertainty that we're input, and look at its square root. Okay, it must be that no matter where the target is, the optimal algorithm, which I'll be referring to as opt, must have a measurement within distance r. Okay, and this is very easy to see by contradiction, right? If it doesn't, then for that particular location, both measurements must be greater than r. Sin theta could be at most 1, so this product would be greater than U star. Right? So that's the first one. So we know that for every location, at least one measurement has to be within this circle of radius r. Okay? And this is something to keep in mind. Okay? Because the advantage of this is it gives us a way to bound the number of measurements in the optimal solution. Okay? And the observation here is something like this. So let's pack as many disks as we can with the condition that their centers are in the area that we want to cover. Okay? So then the number of disks here is a lower bound on the number of measurements that the optimal algorithm must take, right? So pack means that they're disjoint. And we know that for each center, which is in the area, there must be at least one dedicated, one measurement that's different from the other ones. Okay, so and this is kind of the game that we have to play for establishing an approximation bound. What is the lower bound on the optimal solution so that maybe we can compare our performance against it. Okay, so this is the first observation, and this is how we get a lower bound on the number of measurements. We still haven't specified our measurement locations, but now let's talk about the tour length. Okay, because remember we're trying to minimize the total time, which is given by the travel time plus the time for each measurement. Okay, and here's a question for you. So suppose I give you 3 disks of same radius, right? So you can think of like you have 3 quarters, and you want to arrange them so that the tour that visits each circle is as small as possible. Okay, how can this be? How small can this tour get? Can it be 0, for example? Like for 2, it can be 0, right? They could be touching each other, and then so. Well, for 3, can it be arbitrarily small? So it turns out that it can't. There's always a lower bound, which is a function of the radius of this. So if you look at this tiny little tour, this is always a function of the radius, the original radius. Okay. So this is a nice thing, because then if we can say something like the optimal algorithm has to visit 3 non-intersecting disks, then it has to spend some time that's proportional to the radius. So it is not arbitrarily small.
you have to go to the center?
No, the goal here is just to visit the disks. Right? Because all we know is that it has to get in these disks, but we don't know that it has to go all the way to the center.
Somewhat related question. In the packing example there, it seemed from the figure that you could push the circles a little bit more. Like, was that an optimal diagram you're showing, or was that an example?
No, anything you can pack gives you a better lower bound, right? And it could also be, I got lazy in drawing it, but no matter, I mean, the more you can pick, the better, because it's a lower bound, so you're trying to push it as high as possible, right? But so, like, this observation tells us that in terms of the travel time, the optimal algorithm has to spend some time proportional to the number of disks that we have and the radius of these disks, okay? And this is our way of lower bounding the distance traveled, okay? And the other nice thing about this is, because this time is proportional to r, it allows us to add detours, okay? So for example, if you just wanted to add a detour of proportional to r, of length r, then this only increases the cost by a constant fraction, okay? So the idea is this. So let's say this is what we have established, right? The optimal algorithm is greater than n times r plus some constant, right? And let's say you had a solution which had the optimal cost, but then on top of it you added something that's proportional to n times r, right? Then you just plug this in here, and it increases your total cost again only by a constant factor. So if these two are constant, then you haven't blown up your cost by too much. And this all is thanks to the lower bound. We know that opt has to spend this much, and what we're adding on top of it is like proportional to it. Okay? So let's recap what we have so far. So if I give you a packing of these disks on the domain, first we argued that the number of these disks is a lower bound on the number of measurements. So this is the first handle we have on the optimal solution. And then the second one, because opt must visit every disk, and because there's a lower bound for 2 consecutive edges, then we're allowed to add detours of length proportional to the radius per disk. Okay? So this is pretty much like all we need to come up with a way of analyzing what I'm going to describe next. The thing that we're missing here is, right, we cannot say, like I haven't even told you where we're going to place the sensors, and we also need to make sure that there are no uncovered areas in the solution. And it turns out that if you take a disk and then place 3 measurements in a triangle position, their locations it's not that important, but then you can guarantee that the uncertainty everywhere inside this disk is relatively low, okay? And this is because no matter where you are in here, there are always like 2 sensors that give you good uncertainty, okay? And there's an interplay between the radius and the uncertainty, but because we picked r as a function of this u star, then we can guarantee this, okay? So then we're ready for the algorithm. So it goes like this. Pick a point, take everything within distance to r. We know that opt has to have 1 measurement within r, but we're going to put 3 measurements in here. But in return, we're going to cover everything inside here, okay? And then we'll repeat, okay? We'll pick one point, and then keep placing the sensors. But what we know is because we picked this to be 2r, this disk and the disk associated with this one, r is going to be disjoint, right? So our handle on the lower bound will continue. All right? So the algorithm will just go like this. We'll compute these disks, put these triangular sensor positions, and now we'll just compute a TSP tour of them, okay? And this is an approximation algorithm both with respect to the number of sensors and both with respect to the tour that's traveled, okay? So I'll recap the argument, right? Why does this work? We have k disjoint disks of radius r, and we know that the optimal solution must take k measurements at least, and we only take 3 times that, right? So we're within a constant factor in that case. And then the 3 sensors associated with each disk cover the entire 2r disk, so this leaves no uncovered area, together with the invariant that we continue until we go, no point is left, okay? And finally, the tours that we add is at most order of R per disk. So then we can use this to amortize the cost with respect to opt and show that we're within a constant factor of the total cost. Okay, the details are, I mean, the numbers turn out to be something like this. So the total cost is within a factor 30 or so. And then we guarantee 5.5 uncertainty with regard to this coverage cost.
How did you initialize those red points?
It's completely arbitrary. And that's because of the observation that you made. So any maximal packing is a lower bound. Okay, so it doesn't have to be maximum. So you pick a point, pick 3 sensors, delete everything within 2R, and then pick another one arbitrary.
Maybe I missed this, but didn't you still have these parts that were not covered by any circle in the last diagram you showed before this? So didn't you still have parts in between that were not covered?
Right, but those are just the circles themselves. But once I put the 3 sensors, they actually cover the entire 2R, very good question, area. And these are overlapping, so there is no, okay, very good, yeah, thanks. Okay, cool. So this was the algorithm, and I think like one thing that we kind of like to brag about is not only the proof, but we just went out there. This was before the IROS deadline, I think, last year. So we first validated the sensing model to get the uncertainty numbers and so on. And then we designed an algorithm, and this is the algorithm in simulation, the locations that we got. And then we went out there and executed it later on in the summer. And then we were able to show that, so even on a windy day, and this is just raw GPS data, so the trajectory is a little bit smoother, but we could do like desired measurement location, we were off and we took it, this is the true target, and then this is our estimate, and so on. So this is one of the coverage problems that sort of we studied in this context, okay? Of course, like there are many extensions. So here, this was like an offline worst case formulation. So we want to compute offline trajectory so that no matter where the target is, we guarantee. But you can think about the online version where you incorporate measurements. And of course, there's the multi-robot one where then communication becomes an issue. And one result we have in this domain is for localizing a single target. So with two boats. And here I also have a video of the measurement process. So you see the antenna rotating. So it has to span about 5 seconds at each angle to fit the curve. And what's happening here is like 2 boats. They start at the same location. They estimate roughly the target location, and then they figure out where they should move, and then take measurements, and then come back and exchange these measurements, and then repeat. And in this case, we can bound the number of measurements and the total distance with regard to the optimal one. And one interesting feature of the algorithm is it allows breaking connectivity, because they need to go far sometimes. Then they decide where they should rendezvous back. Okay. So in all of these problems, we assume that the targets are stationary. Okay, in this case, problems become more like coverage types of problems. But of course, you may argue that fish are not stationary. I mean, it depends on how they're moving. If it's more like loitering, that's kind of like just noise. You can add it onto it. But there are other formulations. So one possibility is to go the other extreme and formulate it as an adversarial process. So the fish are actively trying to avoid being detected, being localized, and so on. And these are good because they give you worst case guarantees, and we do a lot of work in this area. The downside is they can be sometimes too conservative in terms of the time it takes and so on. And in between, we started thinking a lot about stochastic versions. So suppose the target is doing random walk, so it's not a function of how you move, but how do you even find it? Like, is it more efficient than the adversarial case? Okay, but we have results like this. So this is we recently showed that 3 pursuers are enough in any polygonal environment which can have holes for this one. And by the way, I should advertise, so if anyone's interested in pursuit evasion games, this month's Robotics and Automation magazine will have a toolkit where we wrote about the techniques that we use to solve some of these ones. So it can give you a good starting point, and I'd be happy to discuss anyone interested in this. And last year, we extended some of these results to differential drives. So we can give guarantees for capture using a differential drive. And then for the stochastic one, we have a good understanding of the problem in the 1D, but 2D is still open. Okay? All right, so now here's a test for you guys to see if you're following. So I showed you this picture as motivation, and I've been talking about the boats, right? What's the problem?
The lake is frozen.
The lake is frozen. This is Minnesota. So what do we do about this? Well, when the lake is frozen, it turns out that you can drive on it. So we have systems like this too. So this type of localization problems are the second group of problems. And then the third one is we've been thinking a lot about energy. And in particular, first we worked on optimizing energy consumption, but there we realized you can't really gain much, only a few % improvement. So we started putting solar panels on the boats. And solar panels in open spaces, it's a no-brainer. But once you're in these types of settings, then it becomes interesting, because maybe to go from here to there, you may want to take a detour and expose yourself to the sun more and so on, or go slowly. So we started looking at those kinds of problems. How do we estimate the amount of sun at a given time only using solar measurements? And here we create a coarse reconstruction of the environment, and then knowing where the sun is, we can predict these kinds of maps. Similarly, the ground robot. And in one particular case, this is especially useful, is for the lake. Since we roughly know where the shoreline is, but we don't know the height of the trees, we can estimate them and then generate these types of maps for any given time of the day, and then use them for planning. Okay. And then the last thing here is, so far we were just avoiding the obstacle avoidance problem, but recently we put a sonar on it, and now we're trying to go around the obstacle. And I'll briefly talk about one problem in this domain. And to kind of motivate the problem, do you guys know about this lost cow problem? All right, so the lost cow problem is the following. There's a cow, and it's lost. And it's standing, it's standing in front of an infinite fence, and there's one gate somewhere along the fence. But the cow doesn't know where the fence is. So how can it find the gate as quickly as possible, where the gate is? So any ideas?
Like a wave back and forth.
Okay, so obviously it cannot commit to a direction, right? It has to go. So what's the wave then?
Double the steps.
Why do you double? Okay, so it's very interesting that I think as you study computer science, it kind of becomes part of your thinking. So the reason doubling is a good idea is the following. If you just increase it linearly, right? If you go 1 and then come back and 2, 4, if this is d, right? Then the total distance you travel becomes order of d squared. So if you take the ratio of the optimal one, d to d squared to d, then it becomes unbounded, right? It's order of d. But if you double, the summation is 2d, right? Times 4, depending on how you do it. So if you take the ratio, it's constant. So by doubling, you can actually guarantee bounded deviation from the optimal behavior. Okay. So we kind of. The reason I talked about this is we were interested in this problem. So let's say you're approaching an infinite, not infinite, but very long obstacle, and you want to go around it. How do you do this, right? It could be that you come here, and maybe if you turn this way, you can very quickly go around it. But the other way, it will take you a long time. So how do you find this? And it has the similar flavor. The difference is we have a sonar, so it's like a narrow beam, 10 degree, and then we also have the motion constraints. So we adapted your algorithm to to this case. And let me show you. So this is the system. The sonar is here. And then these are like the parameters that constrain the problem. And our algorithm is sort of like every time we double, we also do this loop. So this incorporates the turning constraints, and it also gives you a scan of the boundary. So this is the boat executing that one of those turn moves. So on a calm day, it's very smooth, like this. And then the experiment was something like this. So the boat approaches here, and we just treat this as an obstacle. So this side is very long, and this side is the side that we want to go around. So you see the red is the sonar returns. So the boat is executing this doubling one. Of course, the shore is shallow, so we get returns before the shoreline. But after kind of a few tries of that going back and forth, it found, and here I think we had a GPS thing, so it straight away put the opening found, and then it worked. So I guess this is all I want to say for the particular project. Again, like the three problems that we work on are search, active localization, and energy. And the idea is to have robust, like long-term navigation operation in unstructured environment. So this project we're wrapping up, but for the next step we have a new like pilot project to actually tag the bear and moose in northern Minnesota. And for that we're not going to use boats, but we're looking at using the UAVs. And the interesting thing here is what you have is like a cheapo handheld receiver. So we just want to be able to use that. And in general, all you really want to do is to do some gradient following. But the signal is so noisy that it's not easy to do this. So we're looking at like robust ways of, if you take a certain step size, then you can figure out which one is closer. So this is like a very coarse sampling of the gradient and so on. And we've been able to show these kinds of, so that's where the target is, and we can kind of merge onto the target. Okay, so let me take some time and talk about the big picture. The goal for my research is sort of like Googling the planet, right? So just like you have a search engine on a browser, suppose you could actually execute queries like this. So give me the nitrogen distribution over my farm, change in crop height over the season, more in the agriculture domain, or in the environmental monitoring domain, like trajectories of all the moves and so on. And one thing that's kind of becoming more and more important is this is not only geometric information, just positions, right? But also there's semantic information. So we're talking about things like apples or the animal trajectories and so on. So this is kind of a long-term goal, but we have made some progress in the context of sort of orchard monitoring. And what we can do is data collection at multiple scales. So it's kind of like at the top level, we fly at relatively high altitudes and we cover large areas. And then we use this as input to a middle layer where we can go into the orchard and take measurements. And then maybe at a fine level, we can do like close-up inspection with a manipulator, like a camera mounted on a manipulator. So this way, we can maybe get closer to this promise of covering very large areas, but at the same time delivering, very fine resolution. So let me show you some examples of this. So this is the University of Minnesota Horticulture Center near our campus, and we get this type of footage. And one thing that's interesting here is like for most aerial images, they're from higher altitude, so the planar is the scene is planar. But here there's significant like height variation. So we have a new like mosaic algorithm which has significantly less distortion than the existing like even commercial ones. So this could be like the output of the top layer, right? And from here you could extract the rows, and this is even easier like if you do something like this. So this type of reconstruction, it's relatively standard if you are willing to spend a couple of hours for bundle adjustment, but we're working on making this real time basically. That's one thing that we've been focusing on. So for the middle layer, and this is what kicked off our current project actually. So we wanted to do orchard monitoring similar to Steve's work. And we started in orchards like this, and then we were able to get footage of this sort. So this is the imagery from onboard. And here, like this is a pretty friendly setup, and we could do pretty decent detection. But you see that the road there is pretty wide and it's not windy. So as we started working more on this, we realized that this is the type of setting that we have to deal with. So then, it gave us motivation to look into both navigation, but at the same time, some of the sensing problems for dealing with specularities, occlusions, and so on. But now, as of like 2 weeks ago, we have pretty robust, fully autonomous navigation with obstacle avoidance. And then we also have a few other platforms where we combine just a LiDAR and a camera, or just a manual platform to collect imagery. So the output of this layer is a much denser reconstruction. So this is a LiDAR plus camera. And we can also, at the semantic level, we can detect the apples. So right now, like we're just about to get numbers, but for this type of footage, we are about 80 to 90% of what's visible in terms of the counts. And then since we have the geometry, we can actually put it on the 3D reconstruction and then give this type of information. So they're colored in different colors to highlight the fact that they're actual objects that you can semantically talk about maybe for grasping. And then this also opens up new metrics for phenotyping, like the number of apples per volume type of thing, which is hard to obtain now. Okay, and then in the finest level, this is our latest IROS paper. So we've been looking into doing visual surveying in settings like this. You see the occlusions, the specularities, and so on. And this really amounts to designing a robust estimator that you can execute existing surveying algorithms. What else? So we do similar things on more traditional corn fields. We estimate the rows and then we use this to plot height maps. But one thing I'd like to mention from an algorithmic point of view is this sort of air-to-ground collaboration. So we've been working on problems like how can we couple the motion of a ground vehicle and an aerial vehicle to collect informative data. And one interesting aspect that at least we had fun thinking about is imagine that the regions that you wanted to sample were far apart. And rather than flying there directly, the aerial vehicle could land on the ground vehicle and then use it as a mule, and then you release it and so on. Then this coupled motion planning algorithm that is something that we've been thinking about. And then the other problem is just going to appear in wafer is the following. Suppose I give you a bunch of cones on the plane. The angle of the cones represent the field of view of the camera you have on board. And the height is the desired resolution, right? So this is the offline version. What is the shortest trajectory to intersect all the cones? So for this, we have an approximation algorithm now. If you give us the cones in advance, and now we're working on the online version, so can we predict these cones and so on. Okay, so this is really, I know it's late in the day. Let me just conclude and I'll show you guys a few more fun things. But so this is something that I should hide from Matt, but I mean, I guess robots can operate relatively efficiently in factory-like environments, but these challenges translate into factory ones, right? Dynamic unstructured settings and so on, farms and habitat. At least this is what drives our research. And one thing that I found, so there are a lot of these challenges that you guys are familiar with it, but big data is the buzzword that that's thrown in more classical computer science settings, right? But one thing that I actually want to argue for is I don't think for these applications we have the luxury of just going out there, gathering data, and then coming home and then processing it. And I think in-network processing is going to be only just in terms of handling this data efficiently will be something that will gain more and more important. I mean, I'm sure you guys can relate, but in field settings, even getting data from one computer to another can sometimes be challenging. And that's it. So I'll thank the sponsors. And then remember, I started by saying it's the blood, sweat, and frostbites of my students, right? So I'll show some examples of it. So this is Josh doing odometry calibration on ice. Similarly, Pratap doing some kind of debugging on snow, and that's Cheng. I think that's 2 years ago, and I suspect there's something going on in the lab where they have the youngest guy and then send them in the water and so on, that they don't tell me what's happening. Because I had earlier pictures of Josh doing things like this. This is Patrick. He, I think, heard some sound and realized that he lost a nut inside the robot, so he had to disassemble and assemble it, things like this. And this is Nargis, who was searching on search problems, and one day I think they lost the boat. So, so he had to put on these waders and retrieve it herself. You know, farm work, I mean, it's known that it's, you know, backbreaking, but also for the research in farm settings could be backbreaking as well. This is kind of a fun anecdote. We had a UAV accident, and then for some reason we had balloons in the car, and these guys, they tried to put together a balloon system for collecting aerial imagery. Of course, it didn't work, so all we have to show is this fun image. And then, you know, for education, this type of work attracts a lot of attention from kids, all ages. But that's, I'm going to stop here and take questions, so thank you all. It's fun.
So you mentioned three models. One is a stationary one, the other is stochastic, and the third is adversarial. You have reason to believe, maybe based on biology, that there are actually some other non-trivial motion models of animals in packs or groups that, and more importantly, would they be useful for your purpose? Or is it enough to think of them as stochastic or adversarial? Like, might there be some group dynamics that you could exploit?
Oh, decoupling. So, I mean, stochastic doesn't mean one thing, right? The simplest one is a random walk. Right. But there are more sophisticated models like the Levy walk that you pick a random direction and go, which in a lot of cases, I think, better models for animal motion. The group dynamics, I mean, of course, for flocking and so on, but I mean, in those cases, I feel like maybe you can pick a representative for the group. That's what a lot of this, you know, work, right? And then you plan for the cluster using those parameters, like the center of the cluster and so on. But yeah, sure. I mean, it's just in my mind, you know, stationary is a special case of the other two, right? And then either it's reacting to you or not reacting to you. That was the taxonomy that I had in mind. Cool.
So the cow propagate.
It's a technical.
The modeling that you did, do you take into consideration because it seems like a lot of the cost is going to be in the turning
Right.
and other aspects other than the straight line distance.
Right. Yeah.
How do you take that into?
So that's where, like, you adjust the step size so that every time you move, you have accumulated enough cost to justify that big turn.
Yeah.
And then going near the line, for us, it's been, so first of all, it's been pretty tricky to estimate the shore from the very narrow measurements. So then we actually operate with two lines. So there's like the clearance that you want to guarantee. And now once you put those lines, the range is about, you know, 10, 15 meters that we have. So then there's not much you can do beyond it. But I think in general, like if you had something like a plane or like an insect, they actually do more like spiral-like. So insects, they home in like this for localization. Cool.
I had a couple questions about locating these cart spawning pools.
Okay.
I guess the first one is if there's any particular selection in which the cart with these transmitters. And I guess the second one is like, what's the algorithm on top of all this? Is it just like clustering and you just assume they spend more time at the spawning pool locations, or is it something else?
So the aggregation, I don't know if it has anything to do with spawning. The aggregation is, I think they do something in the winter for energy consumption. And why, when, or where they aggregate, as far as I know, is not very well understood. Because like in our case, these are metro area lakes. So it could be that maybe one side is closer to the highway than the other, and they're intrigued by the sound, and like it could be things like this. Honestly, for me, we have like I think much about the carp per se. But I think these are all like the kinds of questions that my collaborators ask. So like in warmer winters, they don't aggregate, for example. I mean, I can at least anecdotally say this. And I'm trying to be a little bit careful to not cross my boundary, because some of these things are, people spend years and years to be able to make one statement about it. And then when, we come in there and as engineers say, oh, just model it like a random walk, it's all right. They're like, go away. So, but yeah, sorry, did I answer your question even?
Yeah.
Okay.
Is there some special considerations for the pursuit evasion problem when the evader has to follow some constraints? Like imagine when you want to manipulate something, you can arrange the dynamics parameter for that object, but that has to follow not like arbitrary motion, but subject to a certain family of dynamics.
Right.
You get to pick the one that is most adversarial to the manipulator.
Right. I thought you were going to say the evader can manipulate the pursuer to not capture the evader or something, but so this pursuit evasion literature, it's pretty well split into two groups. There's the one that's more algorithmic, and in those problems dating back to like the Gibas-Latombe, like the visibility-based pursuit evasion, the tendency is to actually make the evader as powerful as possible and still may give some kind of guarantees. And then the other group of work, the title is Dynamic Non-Cooperative Game Theory. So this builds on optimal control types of results, and often like they either give local guarantees where you say like, given these initial conditions, can you converge to one? Or usually the results are numerical nature. But there are some problems where you can, like there's a problem called the homicidal chauffeur problem, where there's a car trying to hit a pedestrian. Even creepier sounding ones like this lady in the lake problem that I mentioned and so on. There's a book by Tamer Bashar from UIUC on this, which gives a good sampling of these problems. As far as I know, dynamic constraints are very, let alone, like the only result I know is our recent result for the differential drive. And that's there's no dynamics in there, right? And the way we solved it is we decoupled turning and going straight and showed that there's still enough room for progress kind of thing. So I think the problems are wide open as soon as you incorporate either these types of motion constraints or sensing. That's another like huge area. So in these results, we assume that they see each other perfectly, but the moment you start adding uncertainty, you kind of have to operate in this like belief space type of things, and that's something that I actually like thinking about a lot, and we have partial results for some formulations.
One of the challenges you mentioned in your slide was active localization. Could you expand on that a little bit? Like if it's a GPS denied environment, for instance, you don't have the landmarks, or do you, like in these structured settings? So what do you have ideas about what you would do?
Yeah, I should fine-tune my terminology, because the moment I say localization, I think 90% people think that you're localizing yourself, right? So by that I meant localizing the target, and you actively control your positions, like the problem that I described. But even for that problem, if you actually couple your localization with the estimation, you can gain some results on that. So like we right now assume that the boats can independently localize themselves, but that has its own challenges. So we started thinking maybe putting a UAV on top of it to get the relative pose between them much more accurately, to get away from that localization problem. But another thing could be to couple it with the joint estimation of the state for everyone, and then you could do active localization in that sense.
Well, should I bring the proceedings to a close? Well, join me in thanking both of you.
Thank you all.
Good stuff.
Thanks.